to my presentation about making domain-specific language a practical reality. My name is Jurriaan Hage. I'm an assistant professor here in Utrecht at the university in software technology. And the focus of this group on software technology is actually programming technology. And well, most of the people in the group work on Haskell, and my talk is also going to be somewhat Haskell oriented. Sorry for that. All right, what's the purpose of my talk is I want to introduce the field of type error diagnosis. So that's one of my specialties. And I want to discuss one way of addressing this problem of type error diagnosis. Of course, I'll have examples that show that type error diagnosis leaves something to be desired. The trick we use is that we actually can change the behavior of the type inferencer that is inside the compiler from the outside. You can script it, as it were, which should sound very nice to people who like dynamic languages. So there's something also for you here. And what I do then is I use that to get domain-specific type error diagnosis for embedded domain-specific languages in Haskell. Now, if this all sounds mysterious to you, I hope I can at least alleviate that problem by telling you what that actually means. So, mostly what I want to do is to give you a glimpse of something that we have made available in Haskell in a restricted setting, but that could also be yours in your favored statically typed languages. Yeah, you need a static type system. But maybe that's this problem that's going to be solved itself as well. So I talk about statically typed languages. So what that means, it comes equipped with an intrinsic type system, which basically checks some properties of your program before being able to compile it, which is different from dynamically typed languages where you postpone these checks until runtime, which gives a performance penalty, but also it prevents you from having to program around the type system, which, for example, is something that people who like dynamic languages don't like. So this intrinsic type system, the idea is that when you have a wild-typed program, yeah, you cannot add booleans to integers because your language prevents that, and you cannot convert objects to strings like in PHP. You just get the string object, which is probably exactly what you wanted. That was a joke. So the idea is that, and also my students, they say that once they know how to program in Haskell, they say, yeah, and once it is type correct, it's actually correct. So that's where the slogan comes from, coined by Robin Milner, who's no longer among us. Well-typed programs can't go wrong. Of course, it's for the right definition of wrong. Yeah, so there can still be pattern match failures and runtime errors in a Haskell program. Don't kid yourself. But you cannot add a boolean to an integer. Well, even that. But when programs, when a compiler says, I won't compile your program, you deserve an explanation, right? I also deserve an explanation when that happens. So, this brings the need for type error diagnosis. The compiler has to explain, what did I do wrong? So that's the field of type error diagnosis. It's how do you communicate to the programmer that and why a program is type incorrect. Why does it fail to meet the specification of the type system? And there's a lot of information you can hope to get. First of all, that it actually is type incorrect. You might say, duh, but like I said, dynamic languages, you don't get any messages. You would also like to know what kind of inconsistency is this, right? You would also like to know what parts of the program contribute to that inconsistency, because parts that don't contribute, I don't need to look at to fix my mistake. So that would be a big help. And finally, sometimes we can even suggest how to fix the problem. Just replace this identifier with that identifier and you're clean to go. Right. Now, as it happens, functional languages, and that's what my group does most of its work on, functional languages have had more problems with diagnosis than others. Why? Because they have higher order functions. There's many more ways in which you can make mistakes. But that has also led to much research into type error diagnosis in functional language, even 20 years ago, 15 years ago. If you look in the literature for OO languages, I know I wrote 2 papers about Java generics and type error diagnosis. And I know a guy who did a PhD thesis on Scala, but could not get any of his work published anywhere. It's very hard to get somewhere in the OO world, it seems. Maybe. And every time you write a paper about it, they say, oh great, somebody is doing something about it, but they don't accept the papers. And that makes people say, well, let's research something else then. But it's surprisingly little, although I think there's a good case to be made that there should actually pay more attention to this, but we'll get to that in a minute. In fact, right now. So there's layman's law, which basically says that systems only become more complicated. We only add features, and the same holds for languages. Languages only grow. I've only seen one case of people wanted to get rid of something in the language. And this is the implicitly quantified let for Haskell. They wrote a paper about it. We want to remove this because it's in the way. And it was rejected everywhere. So for example, Java, we've seen the introduction of parametric polymorphism, or genetics as they call it, in that setting. And look what it did to the error messages. Terrible. You even had that at the time Eclipse Java compiler and the Sun Java compiler neither did agree with the specification of the Java language. And when they did agree, you found, for example, if you experiment a little bit, that it would get completely different error messages for almost the same error. Yeah, so there's something wrong there. Anonymous functions, getting higher order, only complicates matters more. Languages like Scala embrace multiple paradigms. They also have the functional programming paradigm, they have the OO paradigm. The more paradigms, the merrier, it seems. But when I talk to Wardewski, he says, well, we are running into a type wall. They have local type inference, which is actually a pretty complicated algorithm to work with. Even they are sometimes surprised why that certain programs don't compile. And they're experts. And then they know their way around after a while, after usually years and years, you get used to these things. But he says it's still the case that type systems are only becoming more and more complicated. It's like an armament race. We want to catch more and more errors. But whenever you do that, on the other hand, you also have to work on your defenses. You also have to make your compilers explain better what these complicated messages mean. And that's something that does not happen enough. And actually, Wardewski says, I'm worried that people will flock to PHP and Python and not use Scala anymore because they get these terrible error messages. Also, I think there will be a trend that dynamic languages want to become more static. Right? Because dynamic languages are fine. I mean, I use Perl. Python and PHP are too new for me, but Perl is okay. Well,
you're older?
But they grow up. And when I talk to companies, they say, well, we use a lot of Python. But once it gets above a certain size, mistakes creep in that are hard to catch. You get integration errors, integration problems, and there's no tooling that will help them, at least at that time. There was no tooling helping them to find these mistakes. And then you will see that if you want to build big systems, it's better to have the type system handle these contracts for you. Simple contracts, but still, everything that is handled by a compiler does not take up brain space. And then you will also have diagnosis. Yeah, so that's like my introduction here. So let's look at a few type errors to see what the problem is. Also in Haskell, I mean, every language has them. So this is a very simple program for a Haskeller. I guess you can understand the last line. So if I want to check that a string is a palindrome, I just reverse it and see that it's the same string. Nothing wrong with that. I do the reverse by some complicated fold R, which to some people is the same as reduce. And I flip some cons operator, never mind. I always ask my student, is this well typed? Yeah. This is the error you get. Occurs check, cannot construct the infinite type. Yeah, that sounds very familiar to most of you, I guess. And then it says something like list of t, a list of list of list of t. So for some reason there's a value that he thinks should be a list, but actually he sees something that is a triply nested list. All right. All right, but oh well. Let's criticize this error. Yeah? I think I can criticize at least some things. So let's criticize this error. It does not point to the source of the error because actually the error is not in the reverse. The error is actually in here, the logical error. It's a logical error because actually this definition is type consistent, but it's the wrong implementation. But I can only tell by looking at the type. It's intimidating. Infinite type. Occurs check. If you've done Prolog, well, at least you know what an occurs check is. And infinite type is something that, well, we don't tell to our children at least. It's a pretty... So basically it means that there's some recursive equation that only has an infinite solution. It's like a non-terminating type. Scary. Yeah? It also shows an artifact of the implementation. We call that mechanical. Because occurs check is actually something that takes part in the unification algorithm that actually implements the type inference process, blah, blah, blah. It's something that a programmer should not be aware of, that something like an occurs check takes place. Generally, it's not very helpful. And actually, as it turns out, I only misspelled one letter in my program. The fold R should be a fold L, and then everything works fine. Yeah? So you think, well, why can't they just try fold L, see if it works, and if it works, well, maybe it can give a hint, right? Why can't they do that? Well, it can't. Well, it could, because our compiler can. Right. But that's the idea. So, 3 people from Scotland, they gave it some thought. What would be good error diagnosis? Because it's really hard. Eh? It's easy for me to say I do an analysis and it's sound, it's correct, or it's complete. It does everything you want. Yeah, you can prove these properties generally, but good error diagnosis. Well, young Trinder and Wells say, well, first of all, it needs to be correct. I mean, it should not say this is wrong while it's actually right. Yeah, but we take that for granted, I hope. It should be precise. It should not say the whole program is a mistake. You want it to say, well, there is a mistake, to be precise. Otherwise, you have to look for a long time. It should be succinct. It should not mention all kinds of things that are not relevant to the mistake. It should not depend on the implementation, so it should be amechanical. It should be source-based, yeah, especially in older compilers. Nowadays, we don't see that a lot anymore. But it would desugar the program into something internally, and then it would also give an error message in terms of the desugared code, which looks nothing like the original code. And it should be unbiased. So for example, here I take the head of a list. And the list starts with false, and then you get 1, 2, 3, 4, 5, 6, 7. And in some languages this would be fine. False can be coerced to 0, and then 0 can be coerced to the character 0, for example. And then I would have the head of a list of characters. Haskell is a bit picky. So it says, I cannot put a boolean and a character in one list. But it sees the boolean first. And because it sees the boolean first, it will assume that the rest should also be booleans. It won't say, oh, you have 7 characters and 1 boolean. Maybe the boolean is wrong. Yeah? And this is because the implemented inference mechanism in the compiler works in a particular fashion. And it shows up in the error messages. So this is what we call bias. And of course, it should be comprehensive. It should not leave anything out that would be useful for us to know, to diagnose the error. So these are things worth striving for. But in the end, observed quality of an error is subjective. It depends on your programmer's intentions, what you want to solve. What are you programming? Am I programming palindrome? Then this code actually makes sense, right? But if I would change the names here everywhere, it might well be that actually all of a sudden it makes sense to call this one wrong and this would be right, depending on the name of the identifiers, because that basically tells us this was our intention. Palindrome tells us we want to check that the list is a palindrome. But of course, a compiler does not have any knowledge of the world that, oh, wait a minute, you're implementing the palindrome function, then it must be a function from list to list. It takes a list and returns a bool. Yeah? That's not very likely that we can ever do that. If we can do that, well, that's 300-400 years maybe, but I don't think we'll ever get there. There's also many other factors involved, cultural factors. If you are a PHP programmer new to Haskell, you'll make different mistakes and you would like to have different hints and fixes than if you're a Java programmer coming to Haskell or a Prolog programmer coming to Haskell. And this holds for every language. Whenever you migrate from one language to the other, yeah, there are some false friends, for example, that you need to be warned about. We'll see a few examples later. So you might say, well, is then doomed enterprise? Yeah, if we cannot do it right, shouldn't we maybe not do anything at all? I don't think so. But, yeah, so there's a lot to learn, but we also have to be careful. It's very easy to say, I've invented something that improves type error diagnosis. And then the reviewers in the academic world say, well, what does that mean, prove? And then I'm standing there with my mouth full and say, well, I don't know. Right. So, I want to talk actually about domain-specific type error, but I also want to kind of give you an idea of the field. Yeah, there is such a field as error diagnosis and what that means. But I want to focus on domain-specific type error diagnosis. So actually we built a compiler for Haskell, a subset of Haskell called Helium. You can install it with cabal install Helium, cabal install LVM run. So it implements Haskell 98 minus type classes and instance definitions, so it's not a whole lot. But you can do your normal functional programming with pattern matching data types, folders and stuff, you can do that. And it actually, and there are built-in type classes and instance definitions for numerical classes, EQ classes. Yeah, so, but you cannot add your own. That's basically, it's not, we just never did it. And the idea is that we support domain-specific type diagnosis. So what is so that's error diagnosis that is tailored for a specific domain-specific language. So what's a domain-specific language? So Walid Taha, he said, well, these are the 4 properties I'd like to see. The domain is well defined and central to the language. The notation is clear. The meaning, the informal meaning, yeah, there's a manual that explains what it means. So human beings can read it. But, and this distinguishes it from a jargon, the formal meaning is clear and implemented. So there's actually software that implements your domain-specific language. This sounds, of course, very philosophical, everything, but that's not the point yet. One thing that he misses, I think, is that domain abstraction should never leak. And this is particularly the case when you embed a domain-specific language in a host language like Haskell, like we do. So we have, let's say, the language of Parser building. Parser combinators, there's a talk about it later today. So you can build with an embedded domain-specific language, Parses in Haskell. But when you make a mistake, it will not talk in terms of parsers to you. It will talk in terms of the underlying way in which the parsers were encoded in your host language, which is like higher order functions. Okay? So it will not say your parser is, you don't have a parser, it will say complicated function type and complicated function type. We'll see in a few examples in a minute. So this is something that I don't want my domain abstractions to leak. I don't want internal implementation details of my domain-specific language in the host language to be revealed through error diagnosis because my programmers don't know about these things. Yeah, so I've already hinted here at embedded domain-specific languages. If you've read the book by Fowler, he calls them internal domain-specific languages. And what you do is you encode the DSL syntax inside of a general-purpose host language. And there are good languages for this, like Ruby, you have Haskell. Haskell is mediocre, I think, especially in terms of fluency and syntax. C++ has been seen a lot of use with domain-specific language by means of templates. Paul Hudek said that basically domain-specific languages are the ultimate abstraction. You're tailoring your programming language to a particular domain, which makes you very effective and efficient at programming for that particular domain. Now there are some advantages, although some, like Fowler will say that some of these are actually disadvantages. So you have a familiarity with the host language syntax. Many people that want to use DSLs are still programmers already, but they just want to be more effective programming for a particular domain. And then it's nice that they have a certain familiarity with the host language in their DSL. Fowler would say probably that this is completely bogus. He would say, no, domain-specific languages are mostly used for having non-programmers program. Yeah, like the managers, the office managers that should use SQL to compute their average salary over the last 20 years. There is always the escape hatch to the host language, which again he would not like, but some people prefer to have a fallback. So if you did not provide certain facilities in your DSL, then you can still fall back to the host language and implement it directly in there. There's lots of existing libraries. Yeah? What if you would define your own SQL compiler and you have to implement floating point numbers? Yeah, you would like to be able to use somebody else's floating point implementation because it's completely irrelevant to you, but you still want to be able to use them. Yeah, so you can use libraries, compilers, IDEs. There's a lot of investment if you would have to develop your own SQL IDE just for having your own compiler for a SQL. A lot of money involved. So certainly for prototyping, this is useful. But I think another important aspect is sometimes you have an implementation where you want to use EDSLs for multiple domains and combine these. You want to have a regular expression EDSL and a SQL EDSL, and you have some kind of web server EDSL for doing things with the HTTP protocol. And you want to combine these in an application. You can't have separate compilers for each of these and then hope that you can, in some tricky way, combine these, right? So I think these are at least the last three ones are pretty convincing arguments why this is a useful thing to have. But there are challenges, and one of these challenges is domain-specific optimizations, which I will not look at complete at all today. But there's domain-specific type error diagnosis. And of course, they're also costly in the non-embedded setting, but there you have more control because you're basically building a standalone compiler for that particular domain-specific language. You're in control. Still, you have to invest, but you're in control. What I want is to have that control for error diagnosis in the embedded domain-specific language setting. So they can kind of influence the behavior of the type inferencer inside the compiler, but without knowing the internal details of that compiler. Because I might be able to do that because I built the compiler, but most other people that I would like to be able to use this can't or won't. Alright, so we need a very simplified EDSL for parsing. Just for an example. So the idea is that you look at context-free grammar productions like a non-terminal C is either a D followed by a E, or it's a literal A or a literal B. And just take this as a fragment of your context-free grammar. And what we do is we turn it into executable code in Haskell like this, so the D becomes a small d and a small e. I use explicit concatenation here. So this says parse a D followed by parse an E. And D and E are parsers, so they can parse something complicated, which represents, of course, what these non-terminals should represent. But I can also parse a token A and I can parse a token B. So this is the translation from EBNF, extended Backus-Naur form, to Haskell code. So this is executable code. And of course I need to provide the parsers for D and E, but I hope you get the picture. So non-terminals are turned into functions that do the parsing. And you can also add semantics to this by this $. So basically what it means, if you parse a D followed by an E, then something comes out, right? It maybe D parsed the decimal number and E parsed the letter E. Then you have a decimal number followed by the letter E. Then maybe you want to do something with that decimal number, for example. So this function f takes the results of these parsers as an argument and converts it to something else, does some computation with it. So this is the semantics. And for your information, these things we call combinators. But whenever you encounter the name combinator languages, then this is what is being referred to. These things for combining parsers into new ones, that's also why they're called combinators. Right. I only need this $. For the rest of the talk. So applying semantics to the result of parsing. Because I want to give you an example of what we can do in Haskell. But before we do that, let's see what problem are we solving. Or Peter Hintjes, who just gave a talk, said, you have to know what problem are you solving. Are you actually solving a problem? I think we are. So this is a parser that parses lambda abstractions. Where a slash, which is the start of the lambda expression, is followed by a list of identifiers. Then we get a special symbol, arrow, and then we get the body of the lambda. Okay, that's hopefully pretty straightforward. But what happens, I have a function here that does something with the results of the parsing. But what you typically do when you do this is you say, well, all these symbols that I've parsed, like the slash, back, the arrow, I throw away because I don't need them. I already know that this is a lambda. And the only reason why this syntax was there to know that this is a lambda, but now I can throw them away. I only need the names of the variables, and I need the body. And you see here that there is a wrangle missing here, and here there are 3 wrangles, which to me, I know, suggests that of these 4 parsers, only 3 deliver a result that this function here should consume and then produce an output. But I made a mistake. I made a mistake in that I actually want to throw this thing away, but I accidentally wrote a wrangle here, so it's actually passed to the function. The function, however, takes only 2 arguments, and this is where the inconsistency comes from. It gets 3 arguments, but it wants only 2. And this is the error message you get. And that's pretty terrible. So let's criticize it again. Large, complicated. It doesn't even say where the errors are between those types. Yeah, you really have to look for it yourself. That's engineering. Yeah? But that will take only a day or, well, let's say a week, maybe a month in GHC to get that. And there's no mention of parser errors, of parsers. And you think, well, I'm implementing something with Parser. Why doesn't it say anything about Parsers? Why doesn't it say that I delivered too many results for this function? And it happens to be a common mistake. The only thing I need to do is delete and wrangle. That would solve the problem. Alright? So what we did is we redesigned the type system of Haskell, the Hindley-Milner type system for Haskell 98. And we provide hooks with which you can change the behavior of the type system. And probably more importantly, you can attach your own error diagnosis to the constraints that are being solved. So when it sees a mistake, it can say, ah, now I'm not using the default error message, but your error message. And of course I need to explain how you would write that, because of course it can be too cumbersome or complicated. So that's one thing I'll do in a minute. But note one thing, when I take over or change part of the type system, I still want to be sure that I'm still checking something against the same type system. I'm not allowed to subvert the type system, for example. And this is something that we automatically check for. It's surprising that it's actually possible, but it turns out to be relatively easy. The only thing I can do is to change the order of solving whenever that's allowed, and I can change the error messages that are attached. Alright, so how do you do that? Well, in Haskell we have source files called HS, Haskell script, so it's actually a scripting language, I guess. And if you have something like abc.hs, there can be an abc.type file that contains all kinds of directives that tell the compiler how to modify its behavior for things that are defined in your module. And they're automatically imported and used and exported in high files, whatever. Yeah, so that's all cleanly dealt with. So let's look at an example. So we've seen this dollar operator that applies a function to the result of parsing. So you can tell that by the type signature. It says, you give me a function that takes values from type A to B, and a parser that produces A values, and then I apply that function to that A value, and I get a parser for B values. Right? So if I parse ints, and I apply the function even, then I've actually parsed booleans. I may have read an int, but I've converted it into a boolean. Alright? Now what I want to do is I want to have a specialized type rule for all kinds of expressions that use this particular dollar operator. And we do that in the form of a type rule. So we say here, you say, basically this translation is pretty straightforward. You say, if I have x $y, where x and y are any expression, these are not named variables, they're any expression, then x has to have this type A arrow b, which is a function from A to B, and then y has to have this parser SA type.
I don't think my keyboard has those letters.
No, later has them. But we'll see in a minute how this will look in an ordinary text file. Yeah, so this is still, this is still logical deduction systems and math. But we'll see later how this becomes in text. Alright, so this is the rule that, so this is the type rule that is specialized for applications of the dollar operator. And I'm going to rewrite that for a reason that will become evident later. So I'm going to replace this with placeholders, tau1, tau2, and tau3. And oh yes, I know they are not on your keyboard. But they will change in a minute. So basically this is the same thing. So saying that these are placeholders, and here I just say what they actually should be like. So tau1 should be a function type, tau2 a parser, tau3 also a parser. But what you can also see that there's an implicit check that whatever I parse here is the same type as the input of the function. And I want to let go of that for a minute. So I'm going to split up my constraints into 6 smaller ones, which each kind of gives the smallest additional amount of information. So this only says that tau1 is a function for some a1 and b1, but it doesn't know anything about a1 and b1 yet. It's going to discover what a1 and b1 have to be like. And then it will say, oh, tau2 has to be a parser of some s1 and a2 and s2 and b2. And then I can check that s1 and s2 have to be the same, which is the saying that they have the same name here, that a1 and a2 have to be the same, yeah? And that b1 and b2 have to be the same. And this does not change, it's only a matter of representation. Alright, and now we make the step to Haskell, to ASCII text. So this is how you write it in a text file. Right? So my keyboard can handle this. It's a Mac, but it can handle this. So it's the same rule here, except that I use t's for tors. Of course, you can use any name you like, doesn't really matter. And then here we have the constraints, and it also uses these things. I hope this is clear. And now you can attach an error message to each of these constraints. When that error constraint fails to be satisfiable, it will generate that error message. It's as simple as that. So it says, okay, if T1 failed, if this constraint fails, so this expression here doesn't have a function type, maybe it's a string, then you will get the error message, left operand is not a function. And you will get whatever you write there. Yeah, maybe use a function, stupid. Anything you like. It's up to you. You decide. Of course, oh yeah, one thing I need to check is that these things are checked from top to bottom. This is important. Why? Well, for example, here I say that this parser should have has an incorrect symbol type. So I'm using the word parser, note. That makes it domain specific. I can talk about parsers now. And I say here that the parser has an incorrect symbol type. Now, if I had not checked these constraints yet, I wouldn't even know that they were parsers. But I know that they are parsers because the ones that are above that did succeed in being checked. So I can use that information in later messages to make them more specific. Yeah? It would be really stupid if you would say, parser has an incorrect symbol type, and somebody goes to his program and says, but they're not like parsers at all. And that's probably the problem. Yeah? But it's really stupid to say, well, your parsers don't have to. So that's why this order is fixed, but you can change the order in any way you like. And then use that in your messages. Right. Of course, so if you do something like this, you say, well, I want to parse the word hello world here, and I want to change all of the letters to uppercase. That's what happens here. The problem, of course, is that a string is not a parser. It should be token hello world. Then it's a parser for that particular word. And indeed, if we run the error message, we get right operand is not a parser. Is this a good error message? No, not at all. We're lacking location information. We don't just want to know that the right operand of what? And so forth. So of course what you want to add is context-specific information. We want to know, we want to be able to pretty print, what do we know about the expression y? What do we know about the expression x? What are the type that we actually have discovered thus far? What are the values of these type variables that were in our rule over here? Yeah, what are these types that we've actually discovered up to this point? And of course, in this specification, we use that information by interpolating. So you can say, well, what's the position of the expert? So these are things that the Helium compiler knows about, and it can fill that in for you. And when you run it now, you get this error message. The right operand of dollar should be a parser. In the expression, map to upper blah blah blah. The right operand hello world has type string, but it should be parser har string, for example. Yeah, so this is what you can get. And there's lots of variations. You have a lot more control in like when do I do this solving, when do I make sure that this is type correct, when do I make sure that this is type correct, and so forth. Yeah, so lots of, you might say, syntactic niceties, things that make things more flexible. 10 minutes? Right. All right. We have all the facilities in Helium. So there's automatic checks for soundness and completeness. We have phasing for more global control. A nice one that people always love is siblings. So for example, you're a Haskell programmer, or you're a wannabe Haskell programmer, but you used to be a PHP programmer. I'm not saying whether this is a step up or down, but of course you are used to using dot for concatenating strings. Or you're a Java programmer, and now you're moving to the strange world of Haskell, and you're using plus all the time for string concatenation, and not plus plus as it should be in Haskell. What you can do in your type files, you can say that plus 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 and dot are siblings. What means that if it sees an error, if it sees an expression that uses one of these siblings, like plus, like in this expression here, let y equal 2 in empty string concatenated with 2. But of course, to Haskell it means add 2 to a string, which is type incorrect. It will actually try to replace this plus with its siblings to see whether or not any of the other two will work. And if one of them works, only if one of them works. If more than one works, then it won't give an error message, I think. But then it will say, look, maybe you meant this. That's what happened. And this is pretty sexy, I think. And it's completely, it's trivial to implement, so we eat it. And you just have to have the idea, I guess. So we do this, and then you can have these, you can also add these to your specialized type rule files, and it will use the set of siblings that you want it to enforce. Yeah, so you can change that yourself. You say, well, I was a Java programmer, I know I make all of these mistakes, and I would get better error messages. You just write those siblings in there. That I think anybody can do. Specialized type rules are a bit more complicated, but then you're good to go. All right. So now the funny thing is, so now that we come to the final part of the talk, so DomStat. So DomCode was maybe not the first one to use the word DOM in something they tried to do. So I wrote a proposal some time ago called that I abbreviated with DomStat, which stands for Domain-Specific Type Error Diagnosis. I would have liked to have DomStat, but it's too bad. So this is 2015. I wrote a proposal in 2013. So a student started on this, a PhD student. He's hard to work on this, scaling this to complete full Haskell with higher rank types, with type families, GEDTs, all the stuff that actual Haskell programmers use. And even if you don't use them yourself, you use libraries that use them. And Helium can only handle so much. So we want to build this in GHC or in UHC. Doesn't really matter. So you might think, well, is that important? Well, if, for example, if you look at the top 20 packages that have been downloaded and used, you see that a lot of these extensive type system extensions are actually used by all these packages. And that will make everything we do break down immediately. At least we don't know if it's going to work when we just take it over. So we're now building on extending this, and he has been doing that. And I can tell you about two things we've accomplished. So one is to have conditionals in type rules, and the other one is regular tree expressions. And you can play with this at this URL. So this PhD student has implemented something where you can play with this in the latest syntax, because it's always changing. So one of the things is conditional mapping. So in Haskell we have map and fmap to traverse. Yeah? So some functorial thing if you want that. So this is the functorial map, and this is the map. Basically, it applies a function to everything in the list. That's what map does. And fmap does that generalized to multiple container structures. But you might say, why do you have two of these? Why isn't fmap? Or why isn't fmap just called map and there's only one map that works for every functor? Well, because first of all, tradition. Map existed long before people implemented the functor type class. But also, map, if you can look at the error messages that you do when you do something wrong with an fmap, you get something like functor, blah, blah, blah. When I teach my students to program Haskell, I start them on lists and map. Because I don't want the functor, blah, blah, blah yet, because that's in lecture number 8. Right? So, one of the reasons why they're separated is because of error diagnosis. So what we can actually do with our, at least what we want to do with our methodology, and actually with the new rules we can do that, we can just write a specialized type error rule for map applied to lists. So whenever the compiler sees, oh, you're applying fmap to lists, while fmap is itself much more general, there is a specialized type rule that kicks in that will specifically phrase all the error diagnosis in terms of lists and not in terms of functors and stuff. Right? So this is a bit tricky because you need to know, although the program is type incorrect, you need to know with some assurance that you can discover that it's actually a list thing that you're working on. So this is a bit tricky, but we do have solutions for that. I'm not going to show you examples because they're pretty scary. But you can play with them on the Cobalt Heroku app. There are other things like monad comprehensions versus list comprehensions. If you want to have your students program but not use the very generic versions of all the functions that you will actually want to be using later on, you can restrict the compiler, say, well, you can only use particular classes and particular instances for now. And the list goes on. Another one is, but a bit more complicated, is regular tree expressions. So all the patterns that we can use for saying, yeah, I gave you the example, any expression that applies $ to 2 arguments. And x and y can be any expression. That's the idea. So they're placeholders, they're meta variables. You can also say, I want to look at only applications of the function map to its first argument it, which is the identity function, so that's a particular function, and any expression x's. And you can have that kind of flexibility we do have. But there's all kinds of flexibility we don't have. Basically adding repetition and choice to this pattern language. So we also did that. I have an example in a minute. Disadvantage is that if you use this, then you lose the soundness check. We only have quick check to kind of prove that it's sound, but there's no guarantee. We're fixing that. All right. So this is a particular example. We have a expression syntax for expressions for plus, multiplication, and literals. It's a DADT, which means it can be parameterized over its content. So I can have expressions where all the literals are of type float, and then I have an X per float. And I can have expressions where A is an int, and then I have expressions that only work with ints. I cannot mix them. I cannot have a float and a literal float and a literal int in an expression, because then it doesn't know what to choose for A. It has to commit to either float or int. And now you want to write a function that evaluates an expression to the value, like an X per int becomes an int when I do all the multiplications and additions, and an X per float becomes a float when I do all the multiplications and additions. Alright? And so the things that we wanted to do, for example, is we want to express with our type rule that we first verify that all the literals, everything that is in a literal, these A values, are by themselves correctly typed. They could also be wrong, right? Then we want to check that all the literals have the same type. So that all of the types we found for all of the literals in a particular tree, they're all ints, or they're all floats. And then we would like to check that all this, what we found, and because it could be bool. Maybe I built a X per A with bools here, but they're not in the numerical class. I cannot compute with booleans in Haskell, so that would be a problem. And I will check that also, of course. The thing is that I'm doing all these checks here, but I decide on the order in which I make these checks. And I decide on the error diagnosis I give when such a check will fail. And that's my control. Alright. So, to conclude, I've introduced the problem of type error diagnosis, give you examples where I hope you can see that problem rearing its ugly head. I've introduced specialized type rules to achieve domain-specific type error diagnosis, and I've informed you about some very recent developments. So this is all. The latter stuff is all ongoing work. More ongoing work is to have lightweight approaches so that you can directly in the program write your error diagnosis directives, which are a bit less powerful, but maybe it's preferable for some people over these specialized type rule files that are on the side. One thing that we need to do is that this is pretty technical, is that there are features of the type system of Haskell that are separated from the main type inference process, and we cannot have that in our setup. If you want to know about this a bit more, then talk to me afterwards. So we need to talk about integration. Changes to syntax are ongoing. One nice thing is, so I gave a talk like this at Jurriaan in Prague in July. Lots of people were there. For example, Evan Czaplicki of Elm was there, and I talked to him about this, and he thought these siblings were really sexy. So I now have a student just starting to add what we have here to Elm. And hopefully Czaplicki will actually have it in the main compiler, of course, but by itself it's already, for me, I mean, I'm research, it's already an interesting research project because the type system of Elm is slightly different, largely the same as Haskell's, but also in ways slightly different from that of Haskell, and that to me makes it interesting. And maybe we can also make a contribution there. This is what the student also really wants because he loves Elm. And I will also have a student starting on the penalty type languages, so maybe you've heard of these like Achta, Idris, Kok. Also, and there the problem is even harder because you have the compiler actually runs programs in the type system. Yeah, so diagnosing the errors there is much, much harder than it is in Haskell. So that's pretty challenging. So this hopefully gives you an idea of what I've been working on, let's say 12 years ago, 2003, and what I'm still working on. And I now can take your questions. Oh, and then conclude, I guess, with the credits for people who've contributed, and then take your questions. Thank you.
Yeah, so stuff, and you're very interested in this. Not me, I'm asking for a friend. What would be a good, text or book to start learning about this stuff?
All right. So I think the first thing you should do is to get the Helium compiler on your system. But the thing, so do you want to know about type systems, or do you want to know about specialized type rules?
Well, first off, I'd like to understand the syntax in some of your slides.
Right. So would that be like this? That syntax?
No, more of the cursive written.
Oh, you mean the towels and the...
Yeah, that sort of stuff.
Yeah. This.
Yes.
Yeah. So I would say Benjamin Pierce's book, the first one. Benjamin Pierce, yeah. So he has 2 books. And it's pretty long. It's, yeah. And there's a second book, which I think is much nicer, but it's a bit more advanced. But it goes pretty slowly. And you get all the important stuff. The code is in ML, so that's a bit of a bummer, but yeah. But it has all the implementation. I think you can get all the implementations, and then you can play with these implementations. But that's, I think, a good book to start.
So it looks like you've got to have better error messages. You've got like a compiler on top of a compiler, or a compiler before the compiler.
No.
It's not slow things down, but it's doing other set of checks before throwing things
Right.
out to the next. Like you cut it down to 6 different possibilities in this example. Is that not slower checking those than?
It's yeah. So it's a good question. So I can talk about Helium. So first of all, Helium is just a single compiler that does everything for you. There's no 1, 2, 3, 4 compilers, because it also generates code, and we have an interpreter for running it. But of course, that's investment. That's an investment that you have to make. You could also say I do a preprocessor for GHC, and then you can piggyback right on the excellent code that GHC generates. That's one thing. Although it's not as simple as that, because all these things are in separate type files. They have to be stored when you send somebody your compiled module. It has to have the type errors rules in the module, in the .o file, in the object file, and that takes a lot of work. At least if you would want to do that for GHC, that would be the problem, getting that done. But of course, in Helium we've done that because basically we're in control. We built it from scratch, the whole compiler. So that's one thing. Does it slow things down? So one thing that you have to recognize is that actually it always uses the built-in type system, unless you have a mistake. So only when it comes to what we call a binding group, which is like a set of functions that kind of can only be type inferred together. It's a bit technical, but just think of it like that. Only when it sees a mistake there, will it restart the process for only that particular binding group and apply this technology. But binding groups aren't that big. Yeah, so typically, mostly in Haskell, they're like, because every top-level definition is a binding group by itself. So they're all separate. You don't do this for the whole program. It's only for a very small part of your program, typically. Also, I mean, we've measured this, but the effect on, compared to the parsing time, this is negligible. Even doing this all the time is negligible compared to doing this on the parsing. Actually, the funny thing is that Helium actually has a lot of other heuristics built in, not just the ones that you yourself can write, but also things like if I apply a function to an argument of type A and B, but the function first wants a B and then an A, it will actually tell you to switch the arguments. Things like that. For that, we need, that takes some time because, and we have many of these heuristics running around. So actually because we build a pretty elaborate structure for that called the type graph, and that can be pretty costly. So I've seen examples where adding an argument to a function from 4 to 5 arguments all of a sudden made it, boom, go extremely slow. I still don't know, probably a bug, some performance bug somewhere, but that can happen. But as a rule, it's still faster than the interpreter we used to use, like Hage. And it's also faster than GHC, because GHC implements a much more advanced type system, and it does a lot more than we do. So the user experience is not hampered in that sense.
When I'm using symlinks, are you
suggestion?
No.
So how do you handle when, for example, you're using different siblings and you're connected to the same default?
No, so the only thing, we give an error message. We don't, yeah, so somebody gets feedback and then it's up to him to decide, or her, to decide, am I going to apply this fix? Because maybe it's, yeah, one of the things when you make a suggestion to the programmer, there is a chance that you will be wrong. Always. Yeah, it could be that he says, well, no, it's not that I have to replace plus by plus plus. I mean, let's go to the example. If I still have time. Where was it? It's the +2. Wake up. Ah.
Yeah.
Right? So it could also be that I want here to write here double quoted strings. Yeah, maybe. There's lots, and I can always insert a function here that will take it to the right time. Undefined is a very nice function for doing that, although your program will always crash when you run it. So that's how all my students fix their type error messages, by putting undefined in various places. And it compiles. It should run now. Well-typed programs can't go wrong. Yeah, until of course my quick check, automatic checker goes over and says, oh, it did go wrong at runtime. Yeah, so the thing is that what you want, that's what we want, and actually some people are very much against this, like the Joe Wells, the young Trinder Wells people. They say whenever you say something, it has to be right, and I'm okay with being wrong. Let's say 2-3% of the time, if I can help people better in 97% of the time. I'm a bit more practical in that sense. But the thing is, you can be wrong, so we don't change programs. We just say maybe this is the problem, and of course. Helium would be easy to extend to say, well, I have 6 possible diagnoses for your error message. You select the right one. That's also possible. No problem. We don't do it, but it would be easy to do. So in that sense, it's always up to the programmer to make his change. First of all, I think this is didactic. That's a good thing. But also because we can't be sure. Maybe you've used LaTeX or other error correcting parsers. Sometimes it will give an error message because it corrected something that should not have been corrected. You think, what? I did not insert any dollar anywhere. And then it says, yeah, you inserted this. Or actually, it will actually say, dollar was inserted or something. And then later on, we get an error message and it says, well, you don't have an answer for it. Yeah, so I never want to do this. It has to be in the control of the program. First of all, for didactically, but also because I can't be sure that it's right. So you just get an error message, and it's up to you to decide, am I going to change my program because of that, and how am I going to change it? And then you can commit that to your repository if you want. But typically you will compile it again until it gets right, and then you commit it, hopefully.
About the siblings part.
Yeah.
When you want to suggest something to the programmer or to
Right.
the user or whatever.
Yeah.
Imagine you have a dynamic amount of types in your system, which is, I guess, the problem. Do you think we will end up defining these siblings in an explicit manner, or do you think it's feasible to have some sort of dynamic sibling recognition in that? You mentioned you were still investigating in this.
Yeah, but not the siblings. The siblings are pretty straightforward. So the only thing with siblings, what you say is that certain identifiers are easily confused. That's what it says. So whenever you see an identifier and the expression that you use it in is type incorrect, try one of the other ones. Maybe it works. And if it works,
How do you define the other ones in a system that has dynamic types?
oh no, but these are not types, these are identifiers.
But what if you want to do that, something like that, with types or actions or...
Oh,
like that?
oh,
A
oh.
simple example for in on the command line, for example, when you make a type of something like that.
Did you mean Boolean in place of?
Yeah.
Something,
Oh, right. So that people mistake booleans for strings instead of identifiers.
for example.
Oh, right.
They'll-
I've never given that any thought, to be honest.
Okay.
So that's maybe a good suggestion to look at. So it's future research. But thanks for your contribution.
Yes, we're running out of time.
All right.
but
Well, thank you very much again.